Okay. Welcome all of you.
Welcome all of you.
Welcome all of you.
Welcome all of you.
Okay. Welcome all of you for. Am I audible? Yes, Kuldeep sir. Am I
Yes.
audible?
Yes, audible, sir. Audible.
Yes, you are audible.
Okay. Okay. So, welcome all of you for your second session of day 5. So, we have a next session. Our expert is Dr. Kuldeep Singh. So, Dr. Kuldeep Singh has received his PhD degree in computer vision from Delhi Technical University, New Delhi, India, and MTech degree in signal processing from Netaji Subhas Institute of Technology, New Delhi. He has worked as a postdoctoral fellow at the University of Alberta, Canada, where he was involved in the development of deep learning-based functional prototype for agriculture application. Before joining MNIT, he worked at the Central Research Laboratory of Bharat Electronics Lab, that is the BE Lab, Ghaziabad, as a scientist from January 2007 to March 2019. During his stint at BEL, he has worked on a various projects of national importance. He was involved in the software development of different C4I systems for India and foreign defense forces. He was awarded R&D Excellence Award at Bharat Electronics Limited in 2009 and 2011. Dr. Kuldeep's research interests involved various fields including machine deep learning, computer vision, mobile security, biomedical, and he has authored more than 50 publications in this research area. He is currently executing various research and consultancy projects sponsored by various government departments and industry. He is also founder of Deep Life Innovation Private Limited, a deep tech startup developing AI-based healthcare solutions. Now I welcome Kuldeep sir. Over to you.
Thank you, sir.
I think you are presenter, sir. You can share your screen.
So I'll share my screen and please let me know if it is visible or not.
Yes, Kuldeep sir.
Am I audible now?
Are you there?
Am I audible?
Yes, yeah.
Okay.
Can you hear me, sir?
Recording start कर.
Amit sir, can you hear me?
Yes, sir. We can hear you, sir. Yes, sir.
And I hope my screen is visible now.
Yes, sir. Make it full screen.
Yeah, I am doing that.
Yes, sir. Perfectly all right.
Here now. Okay, fine. So yeah, good evening, participants, and thanks, Dr. Amit, for a nice introduction. I think this is fifth day of the FDP, and I am sure you must have gone through the basics of machine learning before this session, and somewhat you must have got a glimpse of healthcare applications, specifically from machine learning perspective. In this particular session, we will be more of focusing on the fundamentals of deep learning, and you must be aware that there are a lot of applications, lot of use cases of deep learning, specifically in the healthcare. The total scenario has been changed after the implementation of deep learning based models, specifically in the field of healthcare. We have seen tremendous progress, we have seen tremendous results and human comparable performance of these models. So before diving into these application areas in the subsequent sessions in the coming days, firstly, we thought of taking care of the fundamental concepts related to deep learning. So in this almost 2 hours hour session, though it is a longer one, we'll see if we can have a small bio break in between. In the next 2 hours, I'll try to address, give you a brief overview of what is deep learning, how it originated, what was the history, and then how it has become a buzzword in nowadays. So that will be the brief agenda of today's discussion, starting from the historical perspectives of perceptron, activation functions. We will be discussing feed forward neural network, then some of the gradient descent algorithm, backpropagation algorithm, then we'll take one case study on image classification, and one of the popular model of deep learning, that is convolutional neural network. We will see how convolutional neural networks work, and what is the use of CNN in the field of image classification. Going back to the history of neuron, and uh, the neuron has analogy with, they have inspiration from biological neurons. In the similar fashion, our brain, our neurons in the brain processes the information. In the similar manner, the artificial neural networks also process information. They are capable of taking decisions, and so basically we can say that artificial neurons are computational building blocks of the neural network. The story started with Maculo-Pitt neuron. These two scientists, Pitts was logician and Maculo was neuroscientist. They basically proposed uh, a computational, very simple computational model of neurons inspired by the biological neuron, and that was in 1940s. You can see the journey of the modern deep neural networks. It took almost 7 to 8 decades to come into this shape, and that's why discussing the history is important here. So coming to the MP neuron, you can see the diagram here. They can take multiple inputs. There is a function g which aggregates the input, and then there's a function f which takes decision based on the aggregation of these inputs. So these inputs could be inhibitory or excitatory, and the output y will be, can be 0 or 1 based on what the function f takes the decision. You can see here in this equation, if the aggregation of these inputs gx is passed through this function f, then it will be 1 if this aggregation is greater than theta, and this output y will be 0 if this aggregation is less than theta. So basically this function f is a thresholding function, and we also call it thresholding logic. So what task this neuron is doing? It is basically checking the aggregation and taking a decision. If this aggregation is greater than certain threshold value, then the output will be excited. Otherwise, it will be 0. So that is one kind of simplest computational model which was proposed by Maculo-Pitts. But the problem with this model is that it can only take Boolean values. We can implement different type of logical gates with the help of MP neuron. As you can see here, this AND function, let's say we are implementing a 3-input AND function. So what will be the thresholding value in this particular MP neuron? So if all of these inputs are 1, then only the output will be 1. Otherwise, if any of these inputs is 0, then the output will be 0. So that's why the threshold here is 3. Similarly, in the case of OR function, let me take the pointer here. Yeah. So in the case of OR function, there are 3 inputs, but here, if any of the input is 1, then the output can be 1. So in this case, the threshold is 1. Now, coming to the decision boundaries here, you can see if we plot these inputs, taking an example of 2-input OR function and x1 and x2, and if you write the equation, thresholding equation of this particular OR function implementation using MP neuron, you can say that if x1 plus x2 is greater than or equal to 1, then the output will be 1. So if we plot a decision boundary on a space where we have 2-dimensional space, since there are only two inputs, x1 and x2. And uh, if there is a decision boundary that will cross through these 2 points, because it will be a line where x1 plus x2 equal to 1. So all the points on the right hand side, or the points lying on this decision boundary, will yield a result of 1, and whatever points are there on the left hand side of this line, they will result as a the result will be 0 in those cases. Similarly, we can draw the decision boundary for AND function, and if there are three input, your decision boundary will be a three-dimensional decision boundary. Now, coming to the limitations of MP neuron, the problem is that it can only handle the Boolean values. How about the non-Boolean values? And also, how to decide the threshold? Every time we need to hand code the threshold. Secondly, regarding the weightage of the input, what if we want to assign more weight or more importance to a particular input? And also, what if the functions are uh, non-linearly separable? So these kind of issues are there with MP neuron, and we cannot implement these cases with the help of MP neuron. So with the limitations of MP neuron, the perceptron was presented, and Frank Rosenblatt presented a classical perceptron model in 1958, which was more general computational model in comparison with McCulloch-Putett's neuron. The basic difference was assignment of the weight to the inputs. We can give more importance to a particular weight, to a particular input. Secondly, uh, there is no limitation of Boolean values now. We can have non-Boolean values as well. And further, this particular model was refined by Minsky and Peppert in 1969, and they called it as perceptron model. Now, let's take an example here with the help of perceptron, how we can implement a perceptron. You can see here we have inputs. As of now, just forget about this x0. I'll talk about it later. Suppose we have inputs x1 to xn, and uh, we can write a thresholding equation here if the aggregated input aggregation weighted aggregation of the inputs is greater than a certain threshold, then the y will be 1, the output will be 1. And if it is less than a threshold, then the output will be 0. And in comparison with the MP neuron, you can see a factor of weight has also come here. Earlier, we were just aggregating the inputs. Rather, here we are aggregating the weighted inputs. And as I told you, these weights basically governs the importance of any of the input. Now, coming to the threshold part, if we bring this theta on the left hand side, and then compare this equation with 0 and consider this theta as 0th weight. So basically your W0 will be minus theta and 0th input can be 1. So this will become a generic version where we are considering the theta as one of the 0th input to this perceptron. So more accepted convention is the aggregation starts from I is equal to 0 to n, where the 0th input is 1 and the 0th weight is minus theta, which is the threshold. Now let's take a simple example of how we can use perceptron. Suppose you want to develop a simple perceptron for predicting whether we would like a particular movie or not. And suppose this decision is to be taken based on three inputs, like x1 is if the actor is Shah Rukh Khan, and the second input is if the genre is thriller, and the third input is if the director is Karan Johar. So based on these three inputs, let's see if the output is y. The output Y tells you whether we are going to like this movie or not. So based on the past viewing experience, we say it is data. We may give a higher weight to any of the input. Suppose someone is a hardcore fan of Saruk Khan, then more weight can be given to the input X1. So W1 will be having higher value in comparison with W2 or W3. And maybe someone is a hardcore fan of director Karan Johar, and in that case the W3 will be having the highest value in comparison with W1 and W2. And then we have to choose this theta carefully. So basically this theta is nothing but the prior, we call it bias, and you can also say that it's prejudice. So any movie buff, uh, any person who don't leave any of the movie, so basically we call them as movie buff, and for them the threshold will be very low. So basically, any movie which is there in the theater, the person, the movie buff person will go to watch. He or she will be watching the movie definitely. In that case, whether irrespective of the genre or irrespective of the actor or the director, in that case the theta will be zero. So basically, the basic difference here in the case of Maculopitz neuron and perceptron, we have introduced the weights, and we have taken the threshold as one of the weight. That means these weights are learnable parameters. Uh, we say that we are training the model, we are training the neural network. That means we are learning these weights. These weights tells you which of the input should be given more weightage. Since we have taken theta as one of the weight W0, that means this theta is also learnable here. That means the threshold is also learnable here. In comparison with Maculopitz, where the theta was fixed, that was hard coded. Here in this case, we can we can learn the thresholding parameter as well. So this is the example, one of the example for OR function implementation using perceptron. This is the truth table, and you can see these are the equations here for different values of x1 and x2. We see that we get the values of w0, w1, w2. So based on this table, we can draw a decision boundary, and we can say that on the right hand side we have the positive examples, and on the left hand side we have negative examples. Means negative examples means the output is zero for these cases. Now, how do we train? How do we learn? How do we find out what are the best values of these WIs or the weights? So, let us briefly discuss the errors and the error surfaces. So, basically, error means there is something expectation of the neural network, and there is something which the neural network is giving as output. So basically the difference between the expected output and the actual output is we term it as error of that model. Now let's see it uh, in a detail. Suppose we fix the threshold as 1, that is -1, and try different values of w1 and w2. Suppose w1 is -1 and w2 is again -1. So you can see where the line is. So basically for the case where w1 is -1 and w2 is -1, there are 3 errors. So 3 of the outputs are wrong, right? And if we take W1 as 1.5, W2 as 0, so there is only one error. That means one of the point is on the wrong side of the decision boundary. And in the case of point 0.5, 0.45 and 0.45, there are three errors. This is the line here, this particular line. That is the decision boundary in case where we are considering W1 and W2 as 0.45. In that case, there are 3 points which are on the wrong side. So basically, this 1 is also on the left hand side. Ideally, it should have been on the right hand side, because the 1 point gives you output as 1. So that's the problem. I mean, that's how you find out the correct decision boundary, and that's the concept of errors. So for different values of these weights, you get different errors. So the whole objective here is to find out the best values of W1 and W2 in such a way that we get zero error. So we are interested in those values of W0, W1 and W2 which results in zero error. So why can't we plot an error surface corresponding to different values of W0, W1 and W2, and then see on the error surface where is the minima, and corresponding to that minima we can find out the values W0, W1 and W2. So that's the typical error surface for suppose we have two parameters W1 and W2. So we are drawing this uh, because we have fixed W0 as -1. So we'll plot different values of W1 and W2. So for these values, you can see an error surface can be plotted, and we can find out which values of W1 and W2 is yielding minimum error on this error surface. So we are interested in finding a particular algorithm which can gives us the optimized or the best values of these weights, which minimizes the error. Now, coming to the next version, which is sigmoid neuron. As of now, you have seen that we have uh, a threshold available as the decising function. The decision is being taken based on thresholding logic, even in the case of perceptron as well as in the MP neuron. But uh, suppose we are developing a model here in which we are deciding whether we want to see a movie, we will like a movie or dislike a movie based on just a single input, that is IMDb rating. And uh, the range of this IMDb rating is suppose from 0 to 1, and we keep a threshold of 0.5. Then we will be liking a movie which have IMDb rating of 0.51. However, we will be disliking a movie which have an IMDb rating of 0.49. So it seems a little harsh that we are liking a movie with rating of 0.51, but not one with a rating of 0.49. So I mean that's not somewhat practical. It's very harsh with a just a difference of 0.02. We are considering a movie which is we are not liking that. So instead of having a harsh threshold that is W0, why can't we have a smoother version of this transition? So this uh, you can see an example here, which is a sigmoid neuron. The blue one is as per the perceptron, where we have a hard threshold at W0. In the case of sigmoid neuron, we can use a sigmoid function or a logistic function as a decision boundary or a decision function for deciding whether the output will be 1 or 0. So there is no sharp transition here around this threshold. And also, the output y is no longer a binary, but it's a real value between 0 and 1, which we can interpret as a probability. So instead of directly saying that we are liking or disliking a movie, we can get a probability of liking the movie. There is a uh, 70% probability of liking a movie. So in this case, it is more practical in comparison with a hard threshold. So that's the concept of activation function or a decision function based on the aggregation inputs. We can implement these a sigmoid function or logistic function. We call them as activation function. Why activation function? Because uh, based on the input, they will activate the next neuron. That's why the name activation function. So these are the depiction of perceptron and the sigmoid neuron, where instead of having a hard threshold, we are basically having a function which will derive the output based on the weighted aggregation of the input. That is how it looks like. It is not smooth, it is not continuous, and it is not differentiable. However, the sigmoid neuron is smooth, continuous, and differentiable. So that's the perceptron, takes several input, gives a single binary output, and there's an activation function here. So I'm just skipping this part because we already have covered this part in detail. Activation functions are here to introduce the non-linearity into the network, because most uh, uh, most of the real world problems are non-linear in nature. So to take decision to solve those problems, we need a non-linear kind of decision function which can solve those problems. So these are some of the examples of activation functions like sigmoid, and nowadays the rectified linear unit, which has become more popular specifically for deep neural network because of the obvious reason. It can train much faster, and then there is a very big problem with larger neural networks that we call as vanishing gradients. So what I want to tell you is, whenever we are training these neural network models, we are calculating the gradient of the error with respect to different parameters. And in the case of these sigmoids, uh, the gradients in the initial layers of those neural networks are almost close to zero, and which basically hinders the training mechanism of the whole neural network. So that's why we say that the sigmoid has a problem of vanishing gradients. However, this rectified linear unit, which is extensively used in deeper neural networks, it prevents from the gradient vanishing problem. Bias we have talked about. So basically now, if we formulate this problem as a machine learning problem, so we do have data, the labeled data. I'm sure you must have studied about the supervised and unsupervised machine learning problems. So if it is a supervised machine learning type of problem, we have data where xi is the input, yi is the corresponding output, and there are n such examples available with us. Our model, our model is uh, uh, is designed to approximate the relationship between this input and the corresponding output. Suppose you want to classify an email, whether this email is fake or genuine. So the decision y is whether it is fake or genuine. X could be different parameters or different features of that email, like the source of that email, origin country of the email. So those could be inputs of that model. Y is the output. Let's say it's a binary classification, then it will be 0 or 1, uh, genuine or fake. So basically, the task of this model is to approximate the relationship, to finalize, to get a mathematical formulation between the input and the output. And so basically, it's a function. It's a mathematical function which has different parameters. This could be like simple sigmoid, uh, or it's a linear relationship between input and output. Then the parameters. So in above case, these W's are basically the parameters of the model, and the point to be noted here is these parameters has to be learned. We need to learn these W's during the training. So whenever we say that we are training a model, whenever we say we are building a model, that means we are finding the best values of these W's or the weights so that we get perfect output Y whenever we give an input X. Now, coming to the learning algorithm, the algorithm for learning these parameters of the model. So there are different algorithms like gradient descent or perceptron learning algorithm. And while implementing this learning algorithm, we need objective function or loss function or an error function to guide this particular learning algorithm. So basically, the learning algorithm should aim to minimize this loss function or the error function. You have seen the examples of error in the previous slides where we were for different values of W's, we are getting different error values. So basically the idea is to find out the best value of W in such a way that the error is minimized. So the whole task of training a model or a learning algorithm is to minimize the error with respect to these weights. Now, the learning algorithm, one of the popular learning algorithm is gradient descent. In the movie example, we can say that Xi is the name of the movie, Y is like or dislike, and the model could be the approximation between X and Y. Basically, since it's a sigmoid kind of model we are using here, it will be a probability of liking. It will give you a probability of liking a movie. Parameter, of course, the weight W. Learning algorithm, we are taking considering gradient descent as one of the learning algorithm. And one possibility for choosing the objective function or the loss or error function could be the mean square error between the expected output. Expected means this yi which was available, the label which was available in the data itself, and y hat is the output which our model is giving during the training process. So in the training process, let's say at the start itself, we will be getting a very high loss or error function. That means we will be this computed output of the model will be very far off the actual output. That means the mean square error between this y hat and this actual output or expected output will be very high. Slowly, we have to change the values of these w's in such a way that this whole loss function is minimized. So there is a mathematical formulation behind this. There is a mathematical way to reduce this loss function, and there is a mathematical way to reduce the value of this loss function with respect to by changing these weight parameters. So basically, how do we learn parameters? We are given inputs. We have a training objective, that is the loss function or objective function we have formulated. You can see here yi is the expected output, which is the label of the input given along with the training data. And then we have a function, uh, the model f, which is being applied on the input xi, and this gives us the whole loss function. Here the loss function is mean square error. We can choose different loss functions for training the models. Fine. Now, how do we train then? What does it mean to train the network? Suppose we train the network with different training examples. So suppose x is 0.5 and the corresponding y is 0.2. We are considering the same movie. We are considering the same movie example. So where output is the probability, and I think no, this is some other data. So in the training example, we have x and y's. So there are suppose two training examples. The first one x1, where x1 is 0.5, the corresponding y is 0.2, and similarly we have the x2 as 2.5 and y2 as 0.9. So at the end of the training, we expect to find W and the bias B in such a way that if we give zero point 0.5 as input to the model, it should give us the output as 0.2. And if we give input as 2.5, it should give us 0.9 as the output. That is what these points are here. But how we are going to achieve this, how we are going to find out the best values of these W's and B. So basically, one way is the layman way. We can try to find out W's and B's manually. Let us try a random guess. Suppose W is 0.5 and B is 0. So let us find out what is the loss value corresponding to these 0.5 and B as 0. So we get 0.073 uh, for these corresponding values by putting uh, the respective x1 and y1 and x2 and y2 here. Then for different values of w and b, we get different values of loss function. So with some guesswork and intuition, we are able to find out the right values of w and b. But now try to imagine a situation where you have thousands of weights, thousands of biases. How are you going to find out the best values of these W's and B's? Here, the example was very simple. We only have two inputs for training. We only have two parameters for training like W and B. But consider deep neural networks or large number of neurons in the neural network. We will be having more and more weights and biases. So learning parameters, one simple way is we plot a error surface and then do a random search on that and try to find out a minimum. But there is more to it. You can see here for different values of these W and B, we are getting different activation function, different sigmoid activation function, and the corresponding error values on this error surface. So finally, we want to find out the best values of these W's and biases so that the error surface is minimized. Now, let us take a simple example here. Let me tell you the multi-output perceptron. So as of now, we were just seeing a single output perceptron, but we can have multi-output perceptrons. We can have inputs from x1 to xk. We have corresponding weights for these inputs. So for input x1 to this first perceptron, the weight will be W11, and for input x1 to another perceptron output, the weight will be different. So again, you can find out the outputs based on the aggregation of the inputs and then activation function being applied on that. So that is how I mean, this is a simple thing. That is how we can find out the outputs for one layer neural network. So if we talk about one layer neural network, means we have one hidden layer and one input layer and one output layer. But if you say a deep neural network, the term deep means it's a deeper network. That means there are large number of hidden layers. There are more than one hidden layer, and of course you have input and output layer. So that's why the term deep neural network. The neural network itself is deeper. We have large number of layers. That means if you have large number of layers, that means large number of neurons, that means large number of parameters, weights and biases, because for each of the neuron you have weight and bias associated. Now coming to taking a simple example of estimating a housing price using a neural network. So suppose in a particular area, you want to find out a price of in a particular city. If you want to predict a price of a house, so you can take multiple inputs, and then you can build a neural network to predict the price. So here it's a multi output perceptron where you have three feature model, and then the corresponding price, and this is the hidden layer in between. So three parameters, three features we are taking here: number of bedrooms, area, and locality. And then how do we train it? So basically we collect large volume of data, and the data is a labeled one. So corresponding to one entry in this table of data, where you have number of bedrooms, area, and the locality, you have corresponding price available with you. So a similar table you can make uh, for the whole data which you have collected. Now the task is to provide this data to this neural network and see what output comes, what this neural network is giving as an output. Then try to find out the error between the output of this model and the expected output. So the expected output here is 30. However, the computed output of this neural network is 20. So there is an error of 10 if we are just considering error as difference between the expected and the computed output. But you can have different kind of error function or loss functions. So the whole idea is to minimize this error so that it is very close to the actual one. So if you do it again and again for all the examples of this table, that means we are training this model. That means we are adjusting the weights here. We are changing the weights here in such a way that this model starts giving the output as the expected output. The whole idea is to minimize this error, this cost function, objective function, or loss function in such a way that the error is minimized. And what is the variable parameter here? What will change? The input is fixed, the output is fixed, only variable is the weight. You have to change the weights in such a way that the error is minimized, the model starts giving the price value as the actual ones. Now, once you have done this training, you can bring new examples and provide it. So this model will start predicting the correct values. Now, taking to a simple feed forward neural network example, you can see here it's a feed forward neural network. Why the name feed forward? Because the inputs are here, the corresponding results will be feed forwarded in this particular network. One, suppose this is one neuron. The output of this neuron will be fed to the neurons in the subsequent layer, and so on. That's why it is feed forward neural network. You can see here we have n dimensional input to the network, that is x1 to xn, and the network contains L minus 1 hidden layers, in this case 2, and each of these hidden layers contain n number of neurons that is equal to the inputs. Finally, there is one output layer where the total number of outputs, the total number of output neurons may be less than the neurons in the hidden layer. And typically, the number of neurons in the output layer are equal to the number of classes in the neural network. So each neuron in the hidden layer and output layer can be split into two parts. You can see here. First, it is pre-activation, and then we have activation. So AIs and HIs are the vectors. So the input layer can be called as 0th layer, and the output layer can be called as Lth layer, because there are total L minus 1 hidden layers. Now try to visualize here. You have n number of inputs, And I told you that we have weights corresponding to each of these arrows. So this x1 is being fed to each of these neurons here. So we'll have a corresponding weight associated with these arrows. So basically the dimension of the weight matrix will be Rn cross n, because there are n number of inputs here and there are n number of neurons in the subsequent layer. So this matrix of weight will be of dimension n cross n. And there will be a bias associated with each of the neuron here. So the dimension of the bias matrix will be Rn. Then we have WL, which is for the output layer. As I told you, we have only k number of output neurons. That's why the matrix of this WL will be Rn cross k, and the biases will be Rk, are the weight and biases for the last layer. I hope now you understood the structure of this feed forward neural network. Now at the pre-activation at the layer I, how will you compute this pre-activation AI? So it will be the aggregation of weighted aggregation of the input plus the bias. So this is BI. Try to recall our example where we discussed perceptron. So this is W0. Here we are categorically mentioning it as bias BI. And this is the weighted aggregation, right? So if we take the example of this particular combination here, this H1 is the output of this neuron. We will talk about it, what exactly this one is. So this HIX is, G being applied over this pre-activation AI. How do you compute AI? This AI is computed as weighted combination of the output of the neurons from the previous layer plus the biases. In this case, the first hidden layer, it will be the weighted aggregation of the inputs plus the biases. So if I is equal to 1, then it will be just X. If I is 2, then we have to consider the post activation. So basically this neuron is divided into two parts, pre-activation and the activation, and the activation function is G. So G is being applied over this weighted aggregation or the pre-activation. Now G can be taken as any of them, sigmoid, 10H, linear, ReLU, or any of them. And finally the output at the output layer is given by Fx is HLX, which is here, is equal to OA of LX. And now we can have different activation function for output layer and these hidden layers. Fine. Simply we can omit the input representations. We can just say that AI is weighted aggregation of the post activation H plus the bias. The activation at the layer I is given as HI is equal to G applied over AI, which is pre-activation, and G can be any of the activation function. And however, in the output layer, we have O of AL, where O can be different from these G activation function. Now, this is the typical machine learning setup. You have data. You have data for training, Xi and Yi. You have a model, Yi, sorry, Yi, which is being computed by applying this F function, which is nothing but the model on the inputs Xi, and try to visualize here this W1 X1 plus B1, this middle one. This is as a result of this one. This W1 matrix applied over this input, which is weighted aggregation of these inputs, right, plus bias. So this B1 is what is the dimension of this B1? This is n. So there are n entries in this matrix B1. And what is the dimension of this W1? N cross n. So this first term corresponding to the input and the first hidden layer. Once we have computed this, we will apply a activation function here, this activation function. We will get h1 as the result of activation, and whatever we get from this activation, we again compute a weighted aggregation and add the bias. So basically whatever we have got here, we have applied G as a activation, again computed the weighted aggregation of this one and added the bias. Then further at this layer, we have applied an activation G, weighted it with W3 matrix and added B3. And at the output layer, we have different activation function, which is O. And that is what we get as an output of this feed-forward neuron. Now, what are the parameters here? The parameters are all these weights and biases at different layers. So these are basically the parameters. Now we have to learn, we have to train this model. That means we have to learn the best values of these weights and biases. So we will formulate an error or loss function in terms of these weights. So if we are considering this mean square error, that means we are basically finding the mean square between the actual and the expected output here. And the whole idea is to minimize this loss function in terms of these weights and biases. So we'll provide n number of training examples and try to find out the best value of these W's, and who will help us in achieving this. There's an algorithm called gradient descent with backpropagation. So I already gave you the intuition of that error surface. So basically we have to minimize this loss function with respect to W. We have to find out a minima on the error surface. So how do we, what is gradient descent basically? So gradient descent is randomly pick, suppose we are just solving a model, we are just training a model where we have only two parameters W0 and W1. So we randomly pick W0 and W1. So we get a loss value. So basically you have defined a loss function. We need to compute a gradient of that loss function with respect to each of these parameters W0 and W1. Then take a small step in opposite direction of that gradient which we have computed and try to find out the new value of this parameter W by this formula. So basically what we are doing is we are reducing the value of these weights with the gradient value, and there is a new parameter, there is a new factor multiplied here, we call it learning rate. So if this neta is having very large value, that means we have very high learning rate or faster learning rate. So there is a trade-off here. I mean, we cannot have a very large value of this learning rate. This has to be cautiously chosen what learning rate is best for this particular model. So basically the gradient descent is how gradient descent works. We initialize W0 and B0. We basically take a random value of W0 and B0 and then run a loop for max number of iterations and update these weights and biases by this formula. And this del wt is nothing but the gradient of the error function with respect to this particular w. Similarly, we update the bias as well. And maybe what we can do is we can represent these parameters as a single matrix and then write the equation in terms of this single uh, matrix. So theta t, the updated theta, which is nothing but W0 and B0, and this is how we compute it. So now in this feed forward neural network, instead of theta WB, we have theta, which has these many parameters, where this capital L is 3. Here, the example which we have taken is for only for two parameters, W0 and B0. But in our model, this feed-forward neural network, we have more number of Ws and biases. Still, we can use the same gradient descent algorithm. Only difference is we need to update all these parameters. Here we are updating only two parameters. Here we have to update all these parameters. So basically here, this theta 0 will be now all W's and all biases, and this will be updated. And what will be this del theta t? It will be a vector of gradients of loss function with respect to each of the parameter. You can see here this gradient is computed, gradient of the loss function is computed with respect to each of the parameter W1 to WL, B1 to BL. Now in this feed forward neural network, instead of theta, we have all these parameters. That's why the del theta t will have all the gradients. Now that is how it is represented now. Now coming to the back propagation algorithm, uh, I think let's have a quick bio break. If I think we have already gone beyond 1 hour, so I suggest let's have a small bio break and then assemble in 2-3 minutes. Okay, welcome back. I hope everybody is back. So I'm continuing where we left before the bio break. Now, next we are going to talk about the back propagation. You must have heard this term repeatedly whenever you talk about neural networks or deep neural networks. Now, what exactly is back propagation? Back propagation helps us in training the model. The term back propagation means basically in feed forward neural network, we are giving the inputs to this neural network. We are computing the output, and based on the actual output of this neural network, we are finding the loss function or the error function, and basically we are back propagating that error to this network. What does it mean? Back propagating means we are computing gradients of this error function with respect to each of the parameters from the output layer till the input layer. So that's why it's an intuition that we are back propagating that error in this network and computing the gradients of this error function with respect to each of the parameters. So now let's focus on this particular weight here. Let me take, yeah. So let's focus on this weight W112. And for the gradient descent algorithm, we need to learn this weight, and also we need to compute the gradient of the loss function L theta with respect to this particular parameter. How we are going to compute this? With the help of backpropagation. Now, only focusing on this particular leg of this feed forward neural network. So we can just focus on this one where we have taken x1 and this particular leg. Now, using the chain rule of derivatives, what we can do is we can write this equation as the derivative or the gradient of this loss function with respect to this particular weight as the gradient with respect to the output, then the gradient of this output with respect to the previous pre-activation, then the gradient of this pre-activation with respect to this post-activation, and so on. Finally, we can reach the gradient of this pre-activation with respect to this particular weight. So basically, with the help of this chain rule, what we have done, we have computed this gradient in terms of gradient in this chain. So we have built a chain of these gradients throughout this leg of this feed forward neural network. So basically, what we can do is we can just compress the chain rule, and suppose we have somehow managed to compute this one using the previous computations. Next, what we have to do, we have to just compute this part. Similarly, if you have to compute the gradient with respect to this particular weight, firstly you compute this one and then compute the gradient of this post activation with respect to this weight, and so on. So that is how, with the help of this chain rule of derivatives, we are able to compute these gradients with respect to the weights which are deeper in the network. So basically, the whole idea is we get a particular value of the loss at the output, then we try to figure out which parameter is responsible for this particular loss or the error. So the output layer says that, hey, you are not producing the desired output. better take responsibility. We say that this output layer is responsible for this loss function. But no, the output layer says, I'm just processing, I'm just doing my part. Whatever I'm getting from the previous layer, I'm just processing that and applying the activation on it as well. So they say that go to the previous hidden layer and the weights below me. Because you can see with this formula, they are just applying the activation on the weighted aggregation of the output of the previous layer and the bias. Further, so we go back, we go here and ask them what is wrong with you. They take full responsibility, but this post activation HL says that, well, please understand that I am only as good as the pre activation layer. So, whatever this pre activation is giving to this post activation H2, it is just processing that. So, basically, there will be a chain. So, how do we address this? Either you talk directly to the weight, this W11, which is somewhere here, or talk to the output layer. This is just the output layer. A3 is the pre-activation here. Then, with respect to this A3, talk to the previous hidden layer, and then previous hidden layer, and then previous one. So that is how we are back propagating the error in this network, not back propagating the error. We, with the help of this back propagation, we are computing the gradient of this loss function with respect to the parameter which is at the initial layers. So that is how the back propagation works. So just the summary of this gradient calculation with the help of back propagation, what do? We have an input, set the corresponding activations for the input layer, feed forward this input. So basically each of your layer computes the output and the activations, then compute the loss and the gradient at the output layer. Once you have done it, use the chain layer to back propagate and compute the gradients with respect to the each variable in each of the layer. That means we have associated weights and biases in each of the layer. We will compute the gradients with respect to each of the variable, and then output the gradient of the cost function with the learnable parameters are used to update the weights using the gradient algorithm, gradient descent algorithm. So that is how we train these neural networks. The whole idea is to compute the gradients, minimize or change the values of these parameters with respect to that gradient. And of course, the learning rate plays an important role, how fast the network will learn. So that is how we train these models with the help of gradient descent and backpropagation algorithms. So now what I'm going to tell you is how, with the help of these neural networks, we can implement a binary classification of an image. So let me take an image of size 28 cross 28. Here we are classifying a image of digits 0 to 9, and the dimension of that image is 28 cross 28. So if we vectorize that image, the size of this vector will be 1 cross 784, and there will be weights associated here, and of course the biases associated here. So basically in the input layer, we will have 784 neurons. Each pixel will be an input of this model, and then we will be applying the weights and biases on these input pixels and compute the pre-activation and the activations in the subsequent layer. And finally, at the output layer, we will have 10 nodes uh, corresponds to each of the digit. Let me directly come to the diagram here. Yeah, fine. So this is an example of digit 9, handwritten digits. These circles are basically the pixels. So if we vectorize it, it will be 28 cross 28, which is 784. Now, coming to the neural network, at the input layer, we have, I'm sorry, we have 784 inputs, and these are nothing but pixels of this particular image. Now, these inputs will be these inputs will be multiplied with the corresponding weights, and the hidden layers, these hidden layers will be computed. I mean, the pre-activations and the activations are being computed for each of the hidden layer. And then further, the second hidden layer, and finally we have the output layer. Since the number of neurons in the output layers are equal to the number of classes, in this case we have 10 classes, each for one digit 0 to 9. And as I told you, this output will give you the probability of a particular digit. So whichever digit will have the highest probability, the image will be classified to that particular class. Now, what is the significance of these hidden layers? How these hidden layers compute the important information from this input to decide which class this input image belongs to. So basically, you can see that this particular digit is a combination of these two parts. And similarly, this 8 is a combination of these two parts. 4 can be divided into these parts. So basically, what we can see here is, with the help of these pixels and weighted aggregation of these pixels, we have subparts of these images. As you can see here, with the combination of some of them, one of the particular digit will be formed. So only those neurons will be activated, and with the combination of these neurons, the corresponding output will be activated. Corresponding activation of corresponding output means the probability will be highest for that particular digit. Further, these small parts which were there on the second layer corresponding to this particular digit, only these two neurons are activated. In the previous layer, let's see which of the neurons are activated, with which of the pixels have contributed to these activation of these neurons, and further these two neurons are activated. Finally, it is being classified. That means this particular neuron will be having the highest probability uh, for, a, for the class. Now, in the previous hidden layer, these subparts are further subdivided. They are combination of the pixels, and that is how it is being formed. So with the combination of different pixels, some of the neurons are activated in the first hidden layer, and further two neurons corresponding to this particular digit, two neurons are activated. It might be possible if we take different digit, more than two neurons are activated. Finally, these two neurons are activating this output neuron, and we are classifying this image as 9. So that is how it works. So basically, only activate the meaningful pixels. I mean, the only activate the the neuron in the next layer. So basically, the particular pixels helps. You can see here, most of the pixels are dark here. Few of them are basically white. Only those will contribute for the activation of the neuron in the subsequent layer. So how positive is this? That is being decided with the help of this activation function sigmoid. So basically, sigmoid is applied on the weighted combination of these pixels and the weights, and if it is greater than certain threshold, then it is activated, and so on. So this particular operation happens for each of the neuron, and some of the neurons are activated, and they basically contribute to the activation of the neurons in the next layer and further deciding which class this image belongs to. So if we talk about the numbers here, the input layer has 784 neurons corresponding to each of the pixel. Here, the number of neurons in the hidden layers are 16. So basically, the dimension of the weight matrix between the input layer and the first hidden layer is 784 cross 16. Plus, there will be biases corresponding to these neurons. So it will be 16. Sorry, the biases will be calculating later. Right now we are just calculating the weights. So these number of weights between the input layer and the first hidden layer, then number of weights between the first and the second hidden layer, since they have same number of neurons, 16. So the number of weights will be 16 cross 16 here. And finally, the output layer has 10 neurons. So the dimension of the weights between the second hidden layer and the output layer will be 16 cross 10. These many weights are there. Further, I told you for each of the neuron we have one bias. So for this first hidden layer we have 16 biases, second hidden layer 16 biases, output layer we have 10 biases. So there are total 13,002 parameters, and now we have to minimize the loss function with respect to these. That means we have to compute the gradient of the loss function with respect to these 13,002 parameters. And we have to find out the best values of these parameters. So we'll be using gradient descent algorithm with back propagation to find out the best values of these weights and biases. And once we have trained the model, if we provide any new example to this model, it will be giving us correct classification. Next, so this was about the neural networks. Now we want to focus on the deep neural networks. We will discuss different deep neural networks, how these deep neural networks works, how these deep neural networks are different from traditional machine learning. So now you must have studied something about machine learning, and in typical machine learning setup, we have handcrafted features. I mean, we have a dedicated step of feature extraction, and then on those features we apply a trainable classifier, and then we get corresponding output. So the problem with these traditional machine learning pipeline, where we have dedicated handcrafted feature extractor, uh, these features are not generalizable. That means if you are trying to implement a problem of face recognition, whatever features you are using for face recognition, they might not be applicable for image classification. So that's the problem with handcrafted features. And also, it is very tedious to find out to compute the handcrafted features. So the idea is, instead of extracting features from the data, why not we learn the features? Why not we train the model in such a way that it learns the data directly, it learns the feature representation directly from the data itself. So basically, this is inspired the way human perceives the scene. It is the human brain who find out the unique features from a particular scene or an image, so that it can take decision on that. It can classify different objects. So in the similar manner, the deep learning is responsible for learning the feature representation. Unlike in traditional machine learning, there was a mathematical computation of features from the underlying data. So why not we can learn a hierarchy of features directly from the data instead of handcrafted features? So that's the basic concept behind deep neural networks. And let me tell you the number of hidden layers. So basically these hidden layers, these neurons are responsible for extracting information from the data. More the number of layers, more rich features we can extract from the underlying data. And as we go deeper into the network, so initial layers are responsible for finding low level features like edges and corners. If we talk about the images, mid level features, they will combine these low level features, and then we have high level features. This example you have seen in the neural networks where we had only two hidden layers, where the pixels were clubbed together to form the part of a particular digit. In the similar manner, if we have a large number of hidden layers, they will be able they will be able to extract important information in multiple stages. Now coming to the same example earlier, where we have done the image classification of a 28 cross 28 image. Imagine an image of size 256 cross 256 cross 3. 3 corresponds to an RGB image. And suppose in the hidden layer, the dimension is 32 cross 32, and you are having 1000 classes. So recall our earlier discussion where we had 13,000 parameters. But if we consider these type of images and the network, we will be having 7.2 billion parameters. And imagine how you are going to train that. So that's very tedious. So with neural network, image classification problem is hard to handle. So what is the solution? In the neural network, they are basically densely connected. You have seen that the input layer is connected to each neuron in the hidden layer. That means there will be n square connections. It means it is densely connected. But do we really need this much information, this much connections to process the image? So that limitation of traditional neural network gave birth to convolutional neural network. Why not we can have fewer weights? Because you have seen the numbers here. You have seen 7.2 billion if we have 25 256 cross 256 image. It's very tough to train a network for this size of image. So why can't we have sparse connections? Why can't we connect only the relevant part to the subsequent neurons? Because the we have an assumption that the nearby parts in an image, they are related to each other. However, the farther parts in an image are not related. So we need not to connect this neuron to these neurons in the subsequent hidden layer. We can only connect the nearby neurons in that image because we assume that the nearby regions are related to each other. But how can we do this? Let's see. So there is a concept of weight sharing in different locations in the image, just weighted sum of a small area of the image. So you must have gone through the concept of convolution. It has been extensively used in filtering, where we are applying a filter on a signal and the information is being passed through that filter. The similar concept we can also use here in image classification. We can have filters and do the convolution of those filters on a small area of the image. And that filter will be responsible for extracting information from that region of the image. And that information will be propagated further to the subsequent neurons. And we can use the same weights or the same filter all across the image. That means we can have weight sharing. Try to imagine in this densely connected network where we have to learn each of the weight, and these number of weights, there are n square connections. Here we have only n number of connections, but there is a weight sharing as well. The weights which are being used here, same weights can be used here. So you can see how the number of weights are reduced here. So the idea is convolutional neural network use convolution instead of dense connections to process the image, take advantage of the structure of our data. Data is our image, and that imposes an assumption that on our model that the nearby pixels of the image are related with each other and far apart are very less related with each other. So that's with that assumption, we go ahead with convolution of the filter on the image to extract the information. Now let's uh, take a closer look here. This particular image, these are the pixels here. What we have done, we have taken a filter here. Suppose it is 4 cross 4. This filter is nothing but it's a 4 cross 4 weights are there, a matrix of weights which are being convolved with this particular region of the image. And as a result of the convolution, it will give you one value here in the subsequent layer. Now we can move forward this filter here and then compute the second value. Since this particular filter or this particular kernel is being convolved all across this image, there is a weight sharing. The same weights are being applied all across this image. And we are computing the convolution of this weight and the input patch. So that is about learning visual features and weight sharing between the filters. And then not only one filter, we can apply multiple filters or kernels. Instead of using only one, we can have multiple of them. So basically, different filters can extract different features. So subsequently, we can have a multi-dimensional feature in the subsequent layer. So that is how the convolution operation works. Suppose this blue one is the patch size. This is the kernel WXYZ. These are nothing but the weights of this kernel, which are the learnable parameters. This is the image 4 cross 4. We are applying this kernel of 2 cross 2 on this image, sliding this all across this image and computing the output. So how do we compute? How do we compute the convolution? So it's element-wise multiplication and then aggregation. So W is multiplied by A, B, X, E, Y, and Z, and so on. That is how we compute the convolution. So suppose we are applying this kind of a filter on this image. It's an identical one. It's a No, it's not an identical one. It's a average filter. So it will blur the image. Similarly, we can have a edge detection kind of filter or sharpen filter. You can have edge filter, and so we can apply convolution all across the image and compute the output of the convolution. So just slide the kernel over the input image. Each time we slide the kernel, we get one value in the output, and the resulting output is called as feature map. And we can use multiple filters to get multiple feature maps. So I think I suggest to conclude for today. There are around 25-30 slides left for convolutional neural network. We will try to cover up that with tomorrow's we will try to cover up that with tomorrow's practical session. Tomorrow we will be doing hands-on session on image classification using convolutional neural network. We will be trying to implement a convolutional neural network for image classification on Google Colab. And so before that implementation, because that implementation will hardly take 1 hour, before that we will be completing convolutional neural network and image classification using convolutional neural network, because this has become a larger theory part today. I would like to firstly complete the CNN part, and then we will do the hands-on session tomorrow. I hope this is fine. So till now, if you have any queries, please let me know. You can write them in your chat box. So,
Yes, participants, we are open for.
so one of the question is how is loss function calculated? Yeah. So as I gave you some examples like mean square error or cross entropy loss. So there are different types of losses which are being used for different type of problems of machine learning. So there are mathematical formulas related to that. Like mean square error is a simple type of loss function. You can use that for for calculation of the loss. Any other question, please?
It seems that
No further question. It seems to be right now, sir. Anyhow, if you have any question, participant, then sir will be joining tomorrow with us from 2 to 4. So at that time also you may ask the question. Okay. So thank you, sir, for joining with us today. Participants, tomorrow schedule, I believe that you know that we would have a morning session start from 10 to 1. Then we have a break of 1 hour. Okay, and then we will have a session from 2 to 5. Okay, so tomorrow we have a session from 10 to 5 with the in between 1 hour break. So request all of you to join on time. Okay, so see you tomorrow, all of you. Thanks for joining us for today. Thank you, Kuldeep sir.
Thank you. Thank you, all of you. Good evening and good night. See you tomorrow. Tomorrow we'll have the practical session.
Okay, thank you, sir.